Hello, everyone. I see some familiar faces, which is great. Welcome back. Okay. Right. So, welcome to COMPOS Year 13. So, how this works? So, unfortunately, we have been able to secure very few new places for Year 13. And the reason is that, Year 13 is a short program. We finish in January, early January. And it's based on previous material, of course. And but yeah, mostly just because we didn't have enough money to accommodate new students in year 13, apart from a small number, which we might be able which might be able to join year 13. Okay, so that's that. That's what's happening. And your first assignment is due on the 29th, so you have 10 more days. I will do 2 webinars, one on circular motion and one on complex numbers. So today is circular motion, and without any further ado, let's start. Okay, we have a nice number of attendees. So I'm going to share my screen. Yeah, so for those of you who are new, I am Vlad Chernov. I am the lead tutor for COMPOS'. I used to be the coordinator for COMPOS', and now I decided to reduce my role just because I enjoy teaching. I don't enjoy doing admin. Okay, so I'm going to share my screen if the system allows me to. Just a second. Yes. Perfect. You should be seeing my screen. We're talking about circular motion, and it's the 19th of September. Yeah, that's correct. Good. Okay, so in the first problem, I would like you to think about it carefully. A car quickly decelerates. So you're sitting in a car and you slam on the brakes. You feel a force. The driver feels a force acting on her. What is the direction of that force? What is the direction of the force that you feel? And what is that force doing to you? So answer in the chat, please. Pushing you back. What is it? What throws you forwards? Pushing her forwards. Okay. Keeping her moving forwards. But inertia is not a force. If you like force, you have normal reaction force, you have tension force, you have gravitational force. What is inertia? Is not a force. Well, I mean, it depends on how you look at it, of course. Yelise, what do you mean by pushing you back? What can you clarify what it means when you say pushing you back? Against the seat, but you decelerate. It doesn't accelerate, it decelerates, it slows down. So you press the brake. When the car quickly decelerates, the driver feels a force acting in the opposite direction of the car's motion. Okay. Carticare. Carticare. In the opposite direction of the car's motion. Opposite direction of the car's motion. But that would be backwards. But you say that you feel like a force is pushing them forward. So which one is it? So you're kind of contradicting yourself. At least that's what I read. You said there's a force in the opposite direction of the car's motion, so that is backwards. Seatbelt pulls you back because you want to go forwards. Ooh, Karim, you are getting places. Yes, the seatbelt pulls you back, and you are being slowed down. So here you are traveling. Let's say you're traveling, and your body is traveling at 20 meters a second. Suddenly, you slam on the brakes, and the seatbelt is now pushing you back with a force F, slowing you down. So the seatbelt causes your body to slow down. Seatbelt causes your body to slow down. Because you are traveling. You're traveling at whatever speed the car is traveling. And the seatbelt pushes you back. Nothing throws you forwards. Nothing's pushing you forward. It's the seatbelt that is pushing you back and slowing you down. So next time you're in a car, just think about it. The car slows down, you're being pushed back by different parts of the car. It could be the seatbelt, it could be the seat. And if you're slowing down, the force is backwards. You can't escape that. Yeah, F equals ma, right? F equals ma. If you're slowing down, acceleration is backwards. That means the force is backwards. There's nothing you can do about it. If you want to slow down, the force has to be backwards. So what is the problem? Why do you feel like you're being thrown forwards? Well, you're not. You're traveling forwards, and it's the car that is being slowed down by the tires. It feels like the car, well, it's like the car is going backwards with respect to you. And you think that you're being thrown forwards, whereas actually you're not. You're trying to move forwards whilst the car is slowing down. So it feels like you are being thrown forwards. So that's the thing. It's not an easy thing to realize. So, and a similar question. You're on a bus. The bus makes a sharp left turn. You feel a force. What is the direction of that force? You feel a force. A force. What is the direction of that force? Of that force. So here's the bus. So there's the wheels on the bus. And then the bus turns left, and this is you. What is the force that you feel? So you're sitting here, these legs, so this is the bench. You're sitting on a bench, and you feel a force. Which way is that force? Action force in the towards the center of the radius of the turn. Yes, that's what it has to be, left. But what is that force? What is the nature of that force? What's causing that force? You've learned well. You have a force to the left because it's the centripetal force. Centripetal force. Change the direction. You feel as if you're being pushed to the right, but it's no, you're not. You're trying to move straight ahead, but the bus is turning, so the bus hits you from the side. You go forward and the bus turns left, the bus moves left, the bus will hit you, right? Leading to the bus turning. Yes, but we're not talking about the bus. We're not asking why the bus turns. I'm asking what causes you to turn, what causes you to change direction. Because you are sitting on the bus, you don't have wheels. Unless you're in a trolley. Inertia causes you to go forwards, like it just go straight ahead. Why would it make you turn? What causes you to turn? Centrifugal force. As I like to say, if you want to make your physics teacher angry, say 2 words. Centrifugal force. If you're in good relationship with your physics teacher at school, you can try that. Okay. Say centrifugal force and ask what they think about it. Because you're not in inertial reference frame. Yes, you are in a non-inertial frame of reference. There is centrifugal force, but it's not a real force. Newton's laws are defined in inertial frames of reference. If we are sticking with Newton's laws, then we are not allowed centrifugal force. Centrifugal force, because in non-inertial frames of reference, Newton's laws don't work. Okay. Please, could you explain the difference with centripetal and centrifugal force? I have done this in a previous webinar, and you're welcome to watch it. So if you go to our channel, so our COMPOS channel, and you go to year 13 webinars, you will find, playlists. You need to go to playlists and year 13 webinars. You will find the explanation of the difference between centripetal and centrifugal force. So I won't be talking about this today. Normal reaction. Thank you. Thank you, Christina. Thank you, Maria. Yes. Thank you. It is the normal reaction from the seat. Yes, it's it's the friction from the seat, or if you have side, if the seat is like this shape, when you normally see in a seat when it's like this, so the side of the seat is going to push you to the left. This normal reaction force. Or if you are sitting and there's friction, there's a friction force. So that's friction and normal reaction. So these are the two forces that cause you to turn. It's the normal reaction from the side of the seat, if you think about it. Or if you're leaning against the window, it's the window that pushes you to the left. So the force from the window, and that's a normal reaction force, of course. It's a contact force. Contact force is either friction or normal reaction. I don't know. Is there any other contact force? Oh, of course, there's buoyancy is a contact force, but yeah. Okay, anyways, I hope that makes sense. If you are turning left, there's a force towards the center of the curve, towards the center of the circle, and that's it, centripetal force. Centrifugal force does not exist in inertial frames of reference, and we will only be looking at inertial frames of reference. Okay. Non-inertial frames of reference, as I already said, Newton's laws don't work, so everything you do is likely to be wrong. What is centripetal force? Centripetal force is the force that causes you to change direction. What is this? Oh, sorry. What is the centripetal force? I forgot my own question. What is the centripetal force? It's friction. It's friction from this with the seat. Friction from the seat, and it's the normal reaction from the side of the seat. Seat. Perfect. Lovely. Show qualitatively that the acceleration of the bus is directed towards the center of the bend. Okay, so how we do this is we draw the trajectory of the bus and we look at two different points. Let's look at point A and look at point B. At point A, the velocity of the bus is like this. And we call it V initial. Let's call it V1. V1. And at point B, the velocity of the bus is like this, V2. Acceleration is the change in velocity divided by time taken. Okay? And change in velocity. Change in velocity is equal to V2 minus V1. V2 is like this, and minus V1. I hope you know how to subtract vectors by now. So this is V2 and this is V1. It's going to be V2. You draw them from the same point, V1, and this vector is V2 minus V1. So it's a vector towards the center, delta V. Delta V is V2 minus V1. So the change in velocity is left, and the acceleration, which is delta velocity divided by t. So you just divide it by delta t, is to the left as well. So acceleration, the average acceleration is towards the center of the curve. Acceleration. Does that make sense? How well do you understand this on a scale of 0 to 10, please? So there's a question. If the force to the center, why do we feel being pulled away from the center? That's a good question. Imagine you were okay, you don't need to imagine. It's actually very simple. So answering your question. So if this is the bus and this is you, and suddenly I move the bus like this. Imagine I move the bus to the left. What do you feel is happening inside? You feel as if you don't feel that the bus is being pushed into your face. You feel is that you are being pushed to the right of the bus. From your point of view, the bus is standing still and you are moving to the right. Because you think because the bus is your reference frame. So you're inside the bus, and if the bus suddenly moves left, you think it's not the bus moving left, you think it's you moving right. Does that answer your question? Moaz. I understand that centripetal forces act towards the center of the circle, but in the case of an object going around a vertical loop, why does the object not fall down at the top of the loop? So there's a question about the top of the loop. Well, you're not falling down because you have velocity, just like a satellite. Why does planet Earth not fall onto the sun? Well, it actually does fall onto the sun, but it falls it falls, but the sun is kind of moving away. So this is the Earth, and there's a force from the sun, but the Earth is moving at what, 30 kilometers a second ish. Don't exactly remember. I think it's 30 kilometers a second. So it's kind of is falling towards the sun. The sun is causing it to turn. The same way the track and the gravitational force are causing the trolley to turn. Does that answer the question? Did the year 12 Compass follow along and they'd say get a certificate but didn't receive it, so they can send me the certificate? I can put this in my files. Yes, just email me, please. Just reply to the email I sent you today, and I will sort that out for you. No, it is the reaction force to the. Is it a reaction force to the right also? What reaction force are you referring to? Reaction from the side of the seat. No, it's left. The reaction force is left. If you're sitting on the bus, the reaction force is to the left. So it's the window. It's easier to imagine the window. The window is pushing you from the right. You're touching the window. Your face is touching the window. The window is pushing you to the left. Inertia is carrying you forward, but the bus is moving in another direction, pulling you with it. Exactly. You got it. Okay. Okay. So that makes sense. They're mostly tens. Okay. So let's start harder stuff. Oh, and of course here, if you actually take the radius of the curve and then you take this angle theta, this angle depends on the speed, of course, because this side is theta divided by 360 multiplied by 2 pi r, but it is also equal to vt, v delta t. So you can use that and you can actually do the calculations, and if you do the calculations properly, you would get that acceleration is v squared over r. So it's a very nice piece of derivation. So if you haven't done it already, please do it. Yes. So derive this. I really urge you to do it because it really helps you understand the idea behind centripetal acceleration. Okay, and now we are moving to quite sophisticated problems. So I've covered easier problems last year. So today I've chosen 4 quite sophisticated problems. I will be going in quite through them reasonably quickly, but if you get really lost, maybe watch the easier webinars first and then come back to this one. All right, so this is a mass making horizontal circles. So literally, if I take a mass on a rope and I start spinning it, that's what it does. It's moving at a constant speed. And the only thing that you know is the length of the rope. and you know the angle which it makes with the vertical. And you are expected to calculate the time it takes to make a full circle. Okay, so let's have a look. So there are two forces acting. So there's the mg force, and there's the tension force. Now, I'll redraw this. I'll break down tension into components. So this is the mg. Now this tension has two components. The vertical component is T, so this is alpha. So this is T cos alpha, and this is T sine alpha. So we know that T cos alpha has to equal to mg. That makes sense. Okay, because vertically it's not moving, it's staying in the same vertical plane. And here, this force is the centripetal force. This is the centripetal force. Petal force. So we write m v squared over r, because we know the formula for centripetal force. And that's equal to T sine alpha. Now, do we know the radius? Well, we kind of do, because this is the L is the length of the rope, and this is alpha. So the radius is equal to the length multiplied by sine alpha. So substitute that in. So mv squared over L sine alpha equals T sine alpha. And I can express T from here. T is mg over cos alpha. So I have mv squared over L sine alpha equals T mg sine alpha over cos alpha. And I can see that m conveniently cancels out. Okay. So I've got v squared equals L G Have I messed up somewhere? No, I don't think so. Okay. LG sine squared alpha divided by cos alpha. Okay, I'll keep that for now because some things are not clear to me. Like, what is the time period? Well, because we know that the time period, we already used capital T, so let's call it tau, t small, time period, is it's the time it takes to make a whole circle. And a whole circle is 2 pi r. So it's 2 pi r divided by the velocity, isn't it? Time period is 2 pi r divided by the velocity. So velocity is the time period. No, sorry. Velocity is 2 pi r divided by the time period. And we can substitute that into here. So it's 2 pi r divided by tau squared equals Lg sine squared alpha cos alpha. And so that's 4 pi squared r squared divided by tau squared equals Lg sine squared alpha cos alpha. It looks like R is L sine theta, so I can simplify that. L, remove the squares. So tau squared is 4 pi squared R cos alpha divided by G sine alpha. So it's 4 pi squared L sine alpha cos alpha divided by g sine alpha. Sine alpha cancels, and the time period is 2 pi square root of L cos alpha divided by g. Does this formula look familiar to anyone? Yeah, it's the time period for a pendulum. Pendulum is time period is 2 pi square root of L over g. That's the pendulum. And this is L cos the alpha. Let's see what L cos alpha is. Well, if this is L, then this length is going to be L cos alpha. So it's literally this length. So this length is L cos alpha. If you call it L, small l, you get the same formula. So the time period of this is going to be exactly the same as the time period of a pendulum, which is slightly shorter, that goes like this. I would urge you to do this experiment at home. It's not the easiest one, but maybe give it a go. So yeah, if L is L cos alpha, then they are equivalent. Second one, find the minimum speed that a time period is the angular velocity. Time period is 2 pi. Sorry, it's the angular. Time period is 1 over f, and f is omega divided by 2 pi. So time period is linked to omega. The thing is, for a fixed rope at a given angle, the omega can only take one value. Just like planets around the sun. If you put a planet on an orbit, it can only have a particular time period. So if there was another planet between Earth and Mars, you definitely know that the year on that planet would be longer than on Earth, but less than that of on Mars. So the distance from the sun determines the time period of your rotation. There is a formula, the second Kepler's law, but yeah. Why does the time period not depend on angular velocity? It's they. I want to say they're the same thing. Of course, they're not the same thing, but if you know one, you know the other. In the case of the vertical loop, again, if we were in the reference frame of the observer on the rotating object, could we explain why it doesn't fall down by considering an outward centrifugal force? Yes, you could. That's how centrifugal force works. The centrifugal force, if you are the moving object, if you are sitting on the pendulum, you are in a non-inertial reference frame. And then things happen. Like things happens in non-inertial reference frames that don't happen normally. Okay, as I said, Newton's laws don't apply in non-inertial frames. Problem 4. Find the minimum speed that a pendulum must have in order to do a full rotation. Consider two cases. Pendulum is on a rod, pendulum is on a string. Okay, so pendulum on a rod. On a rod. So you have a pendulum and you want to push it at the bottom point so that it does a full rotation. What's the minimum speed at the top? V top. What's the minimum speed you can have at the top if you want to do a full rotation? 0, yeah, you're allowed to have 0 speed because you just need to reach the top and then you will automatically roll back. And that's easy. So if you are here, so V bottom, and so the kinetic energy at the bottom goes into the gravitational potential energy at the top. And the gravitational potential energy, so this height is 2L, because if that's the length of the pendulum, 2L. So 1/2 mv bottom squared equals mg2L. And m cancels, and you get v squared is 4gl. So v is equal to 2 square root gl. So that's the minimal speed you need for a pendulum in order to make a full rotation if it's on a rod. Now, consider that the pendulum is on a string. Now, it's easy to imagine if you're in the top position and you're on a string and your velocity is 0, what would happen? String goes slack, it just falls vertically down. So you're not allowed to have 0 speed at the top. And that is the main difference. Because if you stop at the top, you just fall back down. It doesn't work. So you have to have some speed. So in order to understand what what the speed should be, you must consider the forces acting at the top. So at the top position, and there are 2 forces. There's the tension force pulling you down because it's a rope. Ropes don't pull. And there's the gravitational force, mg. So T and mg. And both these 2 forces contribute to the centripetal force. So the centripetal force, the resultant force is equal to T plus mg. So there are 2 forces pulling you down. And the resultant force, because you're moving in a circle, it's mv squared over r equals to T plus mg. Now, it's not r, of course, it is L, because that's the length of the string. Cool. That means you can work out, V minimum. Your minimum force, so if you go slower and slower and slower, at some point the rope goes slack. So the minimum speed is when the rope is just slack. Speed is minimum is when the rope goes momentarily slack at the top position. So T is 0. And you're left with mv squared over L equals mg. You cancel the m, and you have V minimum is equal to root LG. Okay, that's the minimum speed at the top. All right, so you have mv bottom squared over 2 is equal to the kinetic energy at the top, because you still have kinetic energy, mv top squared divided by 2, plus the gravitational potential energy, which is still 2 mgl. So you can cancel those out. V, you can multiply it by 2, vb squared equals v top squared plus 4 gl. So speed at the bottom is speed at the top, which is lg, plus 4 gl. So that is 5 gl. That's squared. So speed at the bottom is square root 5 gl, which is slightly more. Right? If you are on a rope, you need to move faster than when you are on a rod, and that makes perfect sense. If the GP is max at the top, if the kinetic energy is 0 at the top, then it would fall down. But if you still are moving, the gravitational force causes you to turn, and you're kind of moving. Let me demonstrate. So PET energy skate park. I like this thing. All right, so if you want the skateboard, that's unfortunate. I made it too big. If you want the skateboarder to do a full rotation, you have to give them enough speed. So let's say if I roll down the skateboarder from here, no, they shouldn't be sticking to the track. Okay. So let's say I let go from here, and you can see that they fall down. And I need to let go from higher, and then they can almost do a full rotation. So basically you need a certain amount of kinetic energy at the top, or certain speed at the top, in order to make a full rotation. So here you are. Okay. Once again. Okay. But if you start from here, you don't have. Hope that makes sense. But if the GP, where is the top right equation from? This is conservation of energy. This is conservation of energy. Kinetic energy at the bottom is equal to kinetic energy at the top. Kinetic energy at the bottom equals kinetic energy at the top plus rotational potential energy at the top, of course. because at the bottom we assume no decrease potential energy. Why would the tension be zero there? We are trying to stop the rope from becoming slab. Well, that's the limiting value. Right? If the speed is more, you'd have the more speed you have, the more tension you have. The minimum speed to go safely, to go to do a full rotation, is just when the rope is just momentarily for 0 seconds, the rope is slack. Why would the so how come this when the circle was bigger, the skateboard rider fell down? Well, because they don't have enough speed to go through the whole thing. Like they need a certain amount of speed at the bottom. So we're kind of registering their speed when they're at the bottom of the track, right? The higher you start, the higher the speed that you will have here. So if you make this bigger, they just don't have enough speed to go full rotation. They just fall down. That's it. They don't have enough kinetic energy. All right, 5. A pendulum of mass m and the length L is pushed with a minimum speed to do a full rotation. Find the tension of the string as it passes the equilibrium position. Okay, so we already know that for a pendulum on a rope, to do a full rotation, the minimum speed has to be square root of 5 GL. Okay, and it has a mass m, so we just draw the forces acting on the on the pendulum at the minimum, at the lowest position. So there's the mg, there's the tension force T, and we know that the resultant force is, the acceleration is that way because it's moving in a circle. It's moving in a circle, that means there's a centripetal acceleration. So the centripetal acceleration over L, not over R, but over L, is the resultant force. So it's tension minus mg, T minus mg. Because T is pushing up, mg is pulling down. That's it. So tension is mv squared L plus mg. And we already know v. So it's going to be m multiplied by 5gl over L. We can cancel that, plus mg. And that's equal to 6 mg. All right. So in order to do a full rotation, the tension at the lowest point must equal to 6 mg, which is quite significant. Interesting. Yeah. 6 mg. Okay. Answer. T is 6 mg. Okay. How well do you understand the last question? On a scale of 0 to 10, please. So there are two forces, one going up, one going down. The acceleration is known, and then you use Newton's second law, right? So F equals ma. Because you know acceleration is v squared over L, and the resultant force is T minus mg, and that's how you work it out. Lovely. Okay, I like to see tens. Okay, problem 6. Ooh, we might finish earlier today. Okay. A pendulum of mass m and length L is released from point A. The string meets a nail placed at C. Find the tension of the string when the pendulum reaches point B. So what's going on here? So we release a pendulum. It goes, then suddenly the length of the pendulum changes because now the center of rotation is here, and now it makes a smaller circle. So now it is at point B. So this is like a nail. Okay, I hope that makes sense. Well, first I would use conservation of energy to figure out the speed of the nail at the speed of the ball at B. So we use conservation of energy. So the kinetic energy at A plus gravitational potential energy at A equals kinetic energy at B plus gravitational potential energy at B. We can assume that kinetic energy at A is 0, so we don't need that. Gravitational potential energy. Well, if the length of the rope is L, this is mgl equals kinetic energy at B, that's 1/2 mv squared, mvb squared, plus gravitational potential energy. So we know that this is 2/3 L, so that makes it 1/3 L. 1/3 L. So this is 1/3 mgl. So we can write 1/2 mvb squared equals 2/3 mgl, and m cancels. Actually, we don't really need to cancel. And you'll see why. Let's keep it. Let's keep the equation like this. Let's label the equation as equation 1. Now consider forces at B. Very well, yeah. We consider forces at B. So B. So if you're at point B, there's a force to the left, which is the tension force. There's the gravitational force mg, but it doesn't matter. Of course, it does matter because it causes it to slow down. So, but we're only interested in this force, the tension force. So here, the tension force is going to be mv squared over the radius. And the radius is 1/3 L. V squared over R. All right, so and remember I said we won't simplify this because look, from here we can use mvb squared is 4/3 mgl. So I can replace mv squared, mvb squared with this. So it's 4/3 mgl divided by 1/3 L. So L cancelled, third cancels, and it's 4 mg. Interesting. It's 4 mg. So let's add to this question. What is the acceleration? What is the acceleration at point B? Well, there are two accelerations at point B. First, there's an acceleration which we call a normal acceleration. Acceleration normal. And there's an acceleration tangential. which is that way. It's along the movement of the ball. And acceleration normal, the normal acceleration is v squared over r, which is v squared, which is here. V squared is 4/3 GL. Yeah, that makes sense. Is 4/3 GL divided by radius, which is 1/3 L. So L cancels, 3 cancels, and we have 4g. So the normal acceleration is 4g. And the tangential acceleration is caused by the gravitational force. So it's ma equals mg, which obviously a is g. A is g. So you have two types of acceleration. You're accelerating to the left with 4g, and you're accelerating down with g. And your total acceleration is that. So acceleration is square root of 4g squared plus g squared, which is 16 square root 17 g. And you can work out the direction theta. So theta is arc tan 1/4, which is what, 12 degrees? Arc tan. To 5, 14 degrees. 14 degrees. So this is where we go different from the standard A-level syllabus. It's moving in a circle, but the acceleration is not towards the center. So how could that be? You're moving in a circle, and you are at this position, but the acceleration is not towards the center of the circle. The acceleration is that way. Why? How could this be? Like, how does that work? That's not what you've been taught in school. Or was it? Why is the acceleration not towards the center? It is the result of normal and tangential, yes, but that's not what we were told. We were told that if an object is moving in circles at constant speed, the acceleration is towards the center. No? It's gravitational acceleration. Yes, Miraz. It's not moving at a constant speed. It's slowing down. That's why it doesn't apply here. It is slowing down because there's a force slowing it down. So it's not constant speed, Therefore, it is not the centripetal. It's not the situation that you're familiar with from school. The idea is that there are two accelerations. There's the centripetal acceleration, which is towards the center. There's centripetal acceleration, but there's also the acceleration caused by gravity because it's slowing you down. You are moving up in a gravitational field. The gravitational field is doing work on you, slowing you down. So the tau. Okay, so I don't, Maria, I don't understand the tangential acceleration part. Well, imagine you are on a scooter, electric scooter, and there's a popular nowadays. And here you're traveling in this direction, and you're traveling, let's say, at 3 meters a second. And here you're traveling at 5 meters a second. So you have two, you're involving, you have two accelerations. You have the centripetal acceleration, centripetal acceleration caused by changing direction, and that centripetal acceleration is v squared over r. So it will be increasing, of course, because the speed is increasing. That means that the acceleration will be increasing. And the tangential acceleration, also known as linear acceleration. No, let's not call it linear. That will, because the other one is also linear, tangential acceleration. So it's caused by changing speed. So this is the normal acceleration or centripetal, normal. The tangential acceleration, that's the changing speed. And that acceleration is the change in velocity divided by change in time. That's the standard acceleration that you are used to. And then acceleration, the total acceleration, is the square root of a normal plus a tangential. So please keep that in mind. So when I ask in the assignment, when one of the problems asks, what is the acceleration, you're expected to find the full acceleration, because there are two accelerations. The one that is causing a change in speed and the one that's causing a change in direction. And that's really important. Does gravity not speed it up when falling down along the, you mean the left of the orbit? Yes, it does, but that's not what's being asked. That's why it is accelerating in the first place. Yes, because there's gravity here that's causing it to accelerate. Gravitational force causes it to accelerate. An interesting thing happens when the moment it touches the nail, actually, because the speed here and the speed here doesn't change. The speed is the same. But in the first case, the tension is, well, the centripetal force, mv squared over r, and then you have mv squared over r. But it's different r in both cases. So in this case, it is tension minus mg, and in this case is tension 1, tension 2 minus mg. In this case, mv squared over L equals T1 mg minus mg. And here, mv squared over 1/3 L equals T2 minus mg. So here, T1 is equal to mv squared over L plus mg. And T2 is 3 mv squared over L plus mg. So you can see that the tension force changes instantly. The moment the rope touches the nail, the tension force shoots up by 2 mv squared over L, which is quite cool if you think about it. So this is T1 and this is T2. So there's a sudden change in tension. Sudden change in tension. Understand why the kinetic energy was 0? Because you let it go from a pendulum is released from point A. So that means kinetic energy is 0. Velocity increase, but acceleration doesn't. Wait, how does the velocity increase, but the acceleration doesn't? You mean here? If you're talking here, the velocity doesn't change, but the acceleration changes. That is quite an interesting result, indeed. Acceleration. Well, no, actually, it makes perfect sense. What am I saying? Acceleration can change without changing the velocity. It's a momentarily process. Like you're driving in a car with constant speed, so your acceleration is 0. So your acceleration, you're driving at 30 meters a second. That's motorway speed. Driving a second, your acceleration is 0, so constant velocity. And then suddenly you see a food stand. I don't know, what do you see? And you want to slow down, or you suddenly see your exit. You start decelerating. So you press on the brakes. Your acceleration is, I don't know, minus 5 meters per second squared. But your speed is still 30. You didn't give yourself enough time to slow down. So you can have the same velocity but different acceleration. I mean, the acceleration changes without changing the velocity, because that's what happens in the first moment. Of course, then acceleration starts decreasing, but you need time for that. Okay, I'll leave you here. I'll finish here. Please watch the other webinars. Some of them are easier, some of them are more sophisticated. So there are at least 3 webinars on circular motion, I believe. All right. Angular velocity directly proportional to acceleration. The normal acceleration, the normal component of the acceleration. Only this part. This acceleration is omega squared r. But this has nothing to do with omega. All right. Okay. Then see you next week for some maths. You're welcome. Da-da.